Hello everyone, welcome to our differential equation class. In this video we are going to talk about orthogonal expansions of periodic functions, but this time they are going to be expansions in the time variable. So we are going to start talking about periodic signals in the real world and how we can use orthogonal expansions, in particular one specific type of orthogonal expansion called Fourier series expansions. We are going to see how we can use Fourier series to analyze these periodic signals. Then we are going to focus on the example we are going to solve explicitly in this class, which is the mass spring system that is subject to a periodic force. And this periodic force could be any periodic force, and because of this generality we are going to see that we cannot solve this problem with a method we know. We cannot solve it with Laplace transform, we cannot solve it with undetermined coefficients. But what we are going to do is we are going to decompose this periodic force using the Fourier series expansion, and then we are going to solve the resulting equations for each individual term in that series. And then we are going to add up the solutions to obtain the solutions of the problem we are interested in. A similar idea is used later on to solve the heat equation. So that is the plan for today. Let's start with an overview of periodic signals in nature. Many real-world signals repeat in time. So the idea is how we can study them, how we can analyze them. Examples of periodic signals, well, we have everywhere anything related with electric currents, alternating electric currents, for example. Anything with that data signals that involving Wi-Fi, cellular or Bluetooth. Sound waves, for example, music, or a heartbeat rhythms inside the body, or vibrations, for example in buildings, bridges or any constructions. Brain activity involves periodic signals. The stock market, they always fluctuation that they have some periodicity. Weather cycles, everything is related to the 24 hours or a month or a year cycles. So all these phenomena involve periodic signals. And then what is a good way to analyze this type of periodic signals? Well, a good way is with orthogonal series expansions, in particular Fourier series, because this is a very general tool to analyze periodic signals. Any periodic signal can be written in a particular way. Any periodic signal can be written as a linear combination of sines and cosines. One can prove that. For example, if we have a function f of t that is periodic, which means that the values of f of t at the time t are the same as the values of the function at the time t plus one period, or a multiple of the period. This a function with satisfying this property, we call it periodic with period t. So such a function can be one can prove that such a function can be written always if the function is continuous or piecewise continuous, can be written in this form, where is a constant term and then an addition of cosines and sines of this multiples of this particular frequency. That particular frequency is called the driving frequency of the force, and then the force depends on that frequency and multiples of that frequency. So and the multiples of that frequency, they are called harmonics of the driving frequency, and we can rewrite this expression in terms of omega simply by replacing that by omega. This is what we have here. So this type of decomposition of the original signal. This is the original periodic signal in terms of cosines and sines and the constant term, is what we call the Fourier expansion of the function in terms of the Fourier functions. Each particular term in this sum, infinite sum, so given by this coefficient and the cosine, or this coefficient by the sine function, these sine and cosine terms are quantums of periodic behavior. Any periodic behavior in this function is a linear combination of these units of quantum behavior. So these terms, the sine and cosine functions on each term, these are periodic. First of all, they are smooth functions. So they are differentiable. Smooth means differentiable with infinity many times. Infinity many times differentiable. Then each term is also periodic, with the period is a multiple of the original period, because these are the harmonics, because we have this term n over there. Each term are mutually perpendicular to all the other terms. Recall we have seen something like that in previous videos. The differential operator, the derivative operator, this operator acts in a very simple way on sine and cosine. The derivative of the sine is the cosine, the derivative of the cosine is negative the sine. So because of all these properties, sine and cosines are very useful to analyze any periodic signals. Complicated, I would say, complicated signals in time are built by combining these simple quantum vibrations, just like we see here in equation 1. What is an example of everyday example is music. Every musical note or voice signal is a sum of sine waves. We can write sine, or cosines are just sine waves that they are shifted to make a cosine. So we can describe any musical note with just sine waves. For example, a tuning fork. A tuning fork gives a single frequency. We can call it a single note, a single frequency. We can call it a fundamental frequency. Then if you have a guitar and you plug a string, then you're going to have several, so you're going to have the fundamental frequency and several harmonics together vibrating at the same time. And in other instruments, or for example in the human voice, you have multiple fundamentals with multiple harmonics, and everything combined is what we call music. The Fourier analysis, or the Fourier series, allows us to decompose sounds, which are nothing more than a particular type of vibrations in the air, and analyze these frequencies. So this type of analysis is used all the time. For example, when we want to digitalize music in the, for example, MP3 format, compression format, what we do is a Fourier series, and we save these coefficients. So autotunes apps or instrument tuners, they also make use of Fourier series. Speech recognition, you get some input, some voice, you decompose in Fourier quantum of vibration, and you analyze each of these, the contribution of each of these quantums, of each of these terms, sine and cosines. Equalizers, they do something similar. They decompose the music in frequencies, and you can tune individual frequencies. Noise filtering, that's how you identify noise. You split the original sound in Fourier components, then you know what are the Fourier components of the noise, you delete those, and then you have the sound without this noise, and sounds much better. So all these things are possible with Fourier series analysis. And also one could say, it's not proven of course, but one could say that when we hear a sound, what we do inside our brains is a Fourier analysis too, because this is the way we understand the different sounds. So we can summarize saying that the periodic signals are everywhere, and a powerful way to analyze these periodic signals is with a Fourier series expansion. Now let's see how all these general ideas work in a particular problem that we are going to focus on this lecture, which is a mass spring where in that spring is acting a periodic force. So this is our system. Our system is a spring with spring constant K, and we have attached an object with mass m. There is no friction in this case. We have our usual coordinate system, y, vertical, downwards positive. Here is positive, here is negative. This is the equilibrium position. The system is oscillating around the equilibrium position, and we are acting on the system with a force, a periodic force. We want to analyze how the system is going to move when that happens. Well, that depends, of course, on what type of periodic force we have. So a couple of things that we need to mention is when there is no force acting on the system oscillates with a specific frequency that depends on the spring constant and the mass. This is called the natural frequency, and is given by the square root of k over m, natural frequency of the system. So now we act on the system with an external force, and we are going to assume that the force is periodic. So essentially the force at the time t and the force at the time t plus one period, that we are going to call it capital T, is going to be the same for some t positive. We are going to, so what we are saying here is that the force is going to look more or less something like this. So some very strange force. So some very strange force that every interval in time equal to t, capital T, it repeats itself. So this part repeats itself here with I draw in different color, but just to emphasize that this part of the force is exactly the same as this part, and it's exactly the same as this part and that part. And I'm going to work with this force with an extra assumption that I wrote here. The force is going to vanish in 0 and tau. So that is going to simplify the calculations. It's just a particular type of force. So this force is going to vanish at 0 and is going to vanish at this tau, and this tau happens to be the period over 2. This is not an important condition, but it's going to simplify the calculations. How is going to simplify the calculation? Well, in the Fourier expansion that we were talking about before, this type of Fourier expansion, we are not going to have these coefficients, and we are only going to have sine functions, so one can prove it. So we are going to have only sine functions, only sine series. So let's suppose we have such a force. So this is our system. This is our system with a force more or less like this. All right. So how do we describe this system? We describe this system with Newton's equation of motion, as usual. And Newton's equation is, recall, the mass times the acceleration. I'm using our vertical coordinate here, function of time, second time derivative. Then this is equal the forces acting on the object, which is the force due to the spring that we always write it on this side of the equation, so plus k times y, and then the external force on the other side, F of t. And now what I want is divide by m. So oops, I want to divide by this m. So I'm going to introduce a new notation. Small f of t is going to be just big F, so the original force per unit mass. And recall that we have the natural frequency. So the natural frequency omega 0 squared is k over m. So with that, we can rewrite the equation in the way we like it to solve it, which is y double prime plus the natural frequency squared times y equal the force per unit mass. And we are going to solve this problem with initial conditions. So this is a departure from previous videos where we were studying boundary conditions. Now this problem is going to have initial conditions, so this is an initial value problem, and we are going to have 0 initial conditions for the position and 0 initial condition for the velocity. And the whole solution is going to depend, is going to be driven by the force. So, and this problem is going to be a little bit simpler than the general problem, so simpler. This is going to be a simpler problem because we are going to study forces that satisfy this extra condition, that the force at 0 is equal the force at the period over 2, so tau, which are 0. That is going to give us the possibility to use only sine series, and actually the sine series that come from the Dirichlet problem. So we are going to see how we do that. So that is our problem. This is the analytical version of the problem given in the picture. And what are the solutions methods we know to try to tackle such a problem? Well, we know how to solve this equation in chapter 2 in our textbook using undetermined coefficients. But recall, undetermined coefficient works when the force F is nice. It's simple, exponential, a polynomial, a simple sine, or a simple cosine. And look at this force here. It looks nothing like that. So no, it's going to be too complicated in our case, the force, to use undetermined coefficients. We could compute the Laplace transform. Yeah, that's okay, but again, look at this force. It's not easy what the functional dependence of the force actually is, and how we are going to compute the Laplace transform of that. So, in general, the signal is going to be complicated, so it's going to be too difficult to compute the Laplace transform, at least analytically. You can always do it numerically, but this is another way to solve complicated problems, numerical analysis. Or another method that we can use is to decompose the complicated force, the complicated signal, into a Fourier series in terms of infinite terms with the sine and cosine or both. In this case, because of this extra condition, it's going to be only sine functions. So this is what we want to do, but in order to do that, and in order to use all the machinery of Fourier series, which is what we have been using in boundary value problems, what we need to do is we need to generalize what we have done to get this Fourier series in the space coordinate we need to generalize that to the time coordinates. So we need to generalize inner products from space to time coordinates. But this is kind of straightforward as it is done here. We don't need to do it. We could do the calculation assuming everything, that you know everything, but it's better to write everything down so we know what we are doing. So the definition of inner product can be generalized to a time coordinate. So the meaning of the coordinate is not in the definition of the inner product. So given any two functions, these are function of time, but they could be function of x. They are piecewise continuous on some interval. It doesn't matter if the interval is in space or time, as long as the interval is non-zero. Then we define the inner product in exactly the same way as we did it for the space coordinate. Then we are going to have that the functions yn given by sine of n pi t over tau, the tau here, and n equal 1, 2, 3 to infinity are mutually orthogonal in that interval, because the calculation we did for the space coordinate also works for the time coordinate. So the inner product of yn with some n here and ym with a different m is always 0. The calculation we did for the space coordinate works here for time coordinates. Now we are going to introduce a notation. This this quantity here, we are going to give it a name. It's going to be the fundamental driving frequency. So that quantity here, we are going to have a name. So is let's write the name. Is the natural, is the fundamental driving frequency. Driving because it's the force, fundamental because all the other frequencies are going to be multiple of that. So there is no force here, but when we decompose the force, we are going to decompose in terms of these sine functions, and that is going to be the meaning here. Maybe we can write the name when we have the force. So yes, let's write down the name when we have the force. Right now it's just a single term, and we are going to do it later. And with that notation, then let's write down the name when we use this type of functions inside the decomposition of the force. So these functions now they look a little bit nicer because they look like sine of n and multiples of this frequency times t. And here, of course, n is 1 to up to infinity. So what else? Well, what happens when we do the dot product of one of these functions with itself? Well, it's going to be tau over 2, the same calculation we did in the previous video for the space variable. So now, any continuous function, f of t, this is an f. It looks weird, but it's an f. F of t, so that it vanishes at 0 and vanishes at the other side of the interval that we are calling tau, then it can be written in this form. This is what we know from this the simple Sturm-Liouville problem we have solved in a previous video in the space variable. Everything also works for a time variable. And now here, once we have a function, the function can be that is periodic, or can be written in terms of an addition of this quantum of vibrations. Then here the omega is the fundamental driving frequency. That's the name, and then the function contains the fundamental for n equal 1 and all the harmonics, which are the multiples of that frequency. All right, and what is this coefficient here? Well, that coefficient is given by the usual formula from previous videos. All these functions are mutually perpendicular, so that gives us this formula for the coefficients. And recall, we have this quantity, is right there, so it's in the denominator, so we can rewrite that formula for the coefficient. This f hat n are just constants. We could call it Cn, but I chose to call it that weird way. And then we have here 2 over tau, the integral from 0 to tau of course, the function, the force, the original force times the sine of n omega t dt. So given the force, all these coefficients Fn are known. We can compute them given the force. And this coefficient Fn, what they say is how much of the frequency of the harmonic frequency n omega is contained in the signal, in the original signal f of t. So now with these notations, this definition and notations, we are ready to solve the problem we are interested in. Okay, let's see how we can use this Fourier analysis to solve the problem we are interested in, term by term. What that means. Okay, let's write down the problem. The problem is, let's find a function y of t, solution of, recall, we are doing initial value problems today, in some interval for time, 0 tau, and the equation we want to solve is the harmonic oscillator, the spring mass system attached to a force, external force. This force is quite general and can be written as a linear combination of sine functions with coefficients. It's really general. The only condition we have on this force is that it vanishes at 0 and it vanishes at tau, because each term vanishes in those places. And we want the solution of this initial value problem that has 0 initial position and 0 initial velocity. We want the solution that is driven by this force. We have this quantity, the natural frequency of the oscillator when there is no force. And then we have this frequency that is the natural driving frequency of the force. The force contains that frequency right there and all the multiples, sometimes called harmonics. So we want to solve this equation term by term. What do we mean by that? Well, we want to find a function yn of t that is solution of the following equation. The equation is going to be, the left-hand side is going to be the same as we have over there, yn double prime plus omega 0 square yn, and here equal not the whole force, but one single term in this sum. So we are going to put here the coefficient of that term and then a sine function with n, a multiple of the driving frequency times t, of the fundamental driving frequency. And here we are going to use initial conditions for this little problem. And the initial conditions are going to be, of course, that yn at 0 is 0 and its derivative at 0 is also 0. The same initial conditions that we have here for the whole solution. So this is what we mean solving term by term. Yn, this yn that we are looking for, is going to be the solution that is the response for each quantum of driving frequency n omega in the force. The force is decomposed in infinity many terms. Each term is a quantum of, let's say, vibration given by this function. So for each term we are going to solve the equation, and we are going to obtain the response of the system for that particular quantum of vibration. And then the idea is that if we do that, then let's do it here, then the solution that we are looking for, y of t of equation 2. What is equation 2? Well, equation 2 is that, with that. The solution of that equation is nothing more than the addition of these individual responses. It's going to be nothing more than y of t is going to be the sum from n equal 1 to infinity of these individual responses. So that's the idea of the solving term by term. And let's verify now, before we continue, let's verify that actually this is true. So let's verify that. Verify. Before we continue. So we want to find the solution of this problem. And we are saying that we are writing the solution as this sum. Okay, let's write down the solution as that sum. Sum n equal 1 infinity of yn, and that we need to compute two derivatives. And then omega 0 squared multiplied by the sum of this yn. Now what we can do is, first, these derivatives, they go term by term. So these derivatives go here. Term by term. It's a sum of derivatives now. And this factor, we can write it inside. So we have one single sum, and somehow I changed colors. I don't know why. There we go. And then we can write all this as a single sum of the second derivatives plus omega 0 squared, the original individual response terms. But each one of these, because the way we found them, is equal the right hand side of the equation. So this is just nothing more than the sum of the f hat n and then the individual quantums of vibrations. But here we are reconstructing. Now we have that, so we are reconstructing the force, the original force. So this is indeed a solution of the differential equation. So now this function, do they satisfy the initial conditions? That's the only thing we need to check. That is left. Initial conditions. Well, what is this function at 0? Well, it's the sum from 1 to infinity of yn at 0, but each one of these is 0 because that's how we found them. So this is 0, and of course the same happens for the derivative. This is the sum n equal 1 to infinity of the derivatives at 0, but we found this function by asking that condition, so this is 0. So it satisfies the initial conditions, it satisfies the equation, so this is the one way to find the solution. You have a problem with the complicated right hand side that no method works, so what we do is we decompose it in terms of quantum of oscillations, and we solve for each quantum. Notice that the equation here, we know how to solve it because the right hand side now is super simple. It's a constant times a sign. Here we can use undetermined coefficients. Here we cannot, but we can do it on each single term, and this is what we are going to do. So now we have our problem, which is the term by term problem is yn double prime plus omega 0 square yn is equal the single quantum of oscillation sine of n omega t. And now we can use undetermined coefficients. Because the right hand side is simple. How do we solve this problem with undetermined coefficients? Well, now we need to recall how this is done. But this is done first by finding the solution of the homogeneous equation. What is the homogeneous equation here? Well, the yn double prime plus omega 0 square yn equals 0. So I'm going to call this yn homogeneous because it's solution of the homogeneous problem. And notice there is no n anymore. So actually, for all the n's is the same. So we don't need the index n anymore. We only need the index homogeneous. How do we solve this problem, which is the same for every n? There is no n in the equation. Well, y homogeneous is an exponential rt, yes, and that gives us the equation. The equation is r squared plus omega 0 squared equals 0, and we put it on the other side, that then r squared is negative. That means that r plus minus is nothing more than plus minus omega 0 I. And then we have two fundamental solutions. One fundamental solution is y homogeneous 1 of t, which is the cosine of the natural frequency times t, and the other is y homogeneous 2 function of time, which is nothing more than the sine of the natural frequency times t. So these are our solution of the homogeneous problem. Now we can move to the non-homogeneous. So we need to find a particular solution of the non-homogeneous equation. Now the non-homogeneous equation does have the n, and the non-homogeneous equation has a source. Let's call it fn of t, which is the coefficient here, fn hat, and then the sine of n omega t. So we know that in this case we need to guess a solution n, which is a particular solution, which is going to be a combination of sine and cosines. It's going to be a combination of a constant kn sine of n omega t, and then I'm going to put it in a different color, some other constant k tilde n with the cosine of n omega t. Now the equation doesn't have the term with the y prime. Because of that, this term we don't need it in the guessing of the solution. Is k tilde is going to be 0. So I'm not going to write it to save time. You can keep it, and then you're going to find out that this coefficient is 0. I'm not going to write it already. I'm going to guess something. So I'm going to don't write it, and I'm going to guess only the sign part of the solution. But now there is a little problem. There are two possibilities. The first possibility is case A, is that there is a number n such that luckily n times omega, or unluckily n times omega, is actually, so the multiple of the driving frequency is equal the natural frequency. That could happen. If that happens, we have seen in previous videos that this case is called resonance. When that happens, you see this multiple of omega for a particular, and let's call it n0. There is an n0 such that this happened. So when you have the n0 here, this is going to be exactly that. So the function you are guessing is a solution of the homogeneous equation. That cannot be. So that is a wrong guess, and what we need to do in this case is to guess a second guess, np, which is a multiplication by t of the previous guess, isn't it? Okay, but that t here is, well, this is what we need to do, and then we're going to have a solution that in one of the terms, the solution is going to grow in time. Okay, it's a factor of t, it's not a big deal, but actually it is a big deal, because what we are saying there is that the amplitude increases linearly with time, and time goes on, so it can go to infinity. What means is that if this is the response, this function is a response to that oscillation, the response is going to go to infinity. So what is going to happen is that resonance break whatever is what we are describing here, in this case our spring. The oscillations are going to be so big that the spring is going to break. So this is what we mean by resonance break things. There is a famous video which is what happens to the Tacoma Bridge. The Tacoma Bridge is a bridge that was constructed, and they didn't notice that one of the natural frequencies in the system, so one of the natural, that things in real life have many natural frequencies. Our spring has only one, but in real life different things have different natural frequencies, and one of the natural frequencies actually was the same and one of the driving frequencies. Let's see what happens in that case.
Tacoma Bridge, Washington, opened only a few months ago, was built at a cost of over $6 million. But misfortune overtakes the great structure. These are some of the most amazing pictures ever recorded by a newsreel. The actual collapse of the world's third largest suspension bridge. Only at 35-mile-an-hour wind is blowing, but this apparently sets up a rhythmic swinging of the bridge, which increases with each swing. Finally, the swinging road and the suspension cables give way and plunge into the water below. Fortunately, the only casualties were a car stalled on the bridge and a dog.
Hopefully we now have a better sense of what this factor t actually does in the solution. And we really want to avoid this type of cases, so we are going to assume that our force doesn't have a multiple of the driving frequency equal to the natural frequency of the system. Here in this calculation we assume it. In real life, what we need to do, if you are trying to build that bridge and you don't want to be like the Tacoma Bridge, you need to build your bridge in a way that the natural frequencies, what you can control now is the natural frequencies of your bridge, depending where you put the feet of the bridge, how you hang the bridge, what are these distances. These distances here you can control what is omega 0, and you make it in such a way that this condition never happens, because now you know what happens if they do match. All right, so but in our problem we are going to assume that everything is fine, and we are in what we call case B, and case B is the case where n all the multiples of the driving frequency are different from the natural frequency. So for all n equal 1 to infinity. So in that case, we are perfectly fine why NP, the particular solution, is going to be nothing more than a multiple of the sine of n omega t. So we assume that we are in case B, sorry. We assume case B, and we continue happily our calculation. So what do we need to do? We need to compute the second time derivative of this function, but this is going to be nothing more than negative n squared omega squared, same function, and then we put that into the equation. So we put it into this equation here, we put it there, and this equation is going to tell us what is the factor k, the undetermined coefficient. So we have the second derivative is going to be minus n squared omega squared, then we have the constant k, then we are going to have a sine of n omega t. This is the second derivative, so let's put it here. This is y np second derivative plus omega 0 squared. Now we put the function, which is kn sine of n omega t. Just to be extra clear, this here is nothing more than y np, and all this has to be equal the force, the particular quantum of force, which is the constant times the sine of n omega t. And of course we do that because this function with this function with this function, they cancel out. Then we can pull common factor kn, and then we are going to have minus n squared omega squared plus omega 0 squared, and all that has to be equal this constant that comes from the force. So we obtained the undetermined coefficient. It's been determined and is given by Fn over omega 0 squared minus n omega squared. And there it is. The undetermined coefficient is useful to solve each of the terms in the equation. And now we have our solution ynp. The particular solution for the nth term is going to be nothing more than that. Here is n, and here we're going to have omega 0 squared minus n omega squared multiplied by the sine of n omega t. So this is how the system is going to respond to the quantum of oscillation in the force. To this quantum of oscillation in the force, the system is going to respond with this factor here. So now, is this particular solution the whole solution? Does it satisfy the initial conditions? So 3, we need to check the initial conditions. And what is the first initial condition? We need to check what is this solution at 0. Well, it's going to have a 0 here, so a 0. So satisfies the first condition, great. Does it satisfy the second condition? Well, we need to compute what is the derivative. Ynp derivative is going to be f n hat n omega, and then we have a cosine of n omega t, which is bad news because that is not going to be 0 at 0. Omega 0 squared minus n squared omega squared. So obviously from here the ynp prime at 0 is different from 0. So no, it doesn't satisfy the initial condition. How we can make it that the solution satisfies the initial condition? Well, we need to add on each term solution of the homogeneous equation. That's how we always do it. So we write, so this is the particular solution. You see, yn particular. So the solution is not the solution we are looking for because it does not satisfy the second initial condition. So the solution we are looking for is going to be a combination of a cosine of the solution of the homogeneous equation, which is omega 0 t plus C2n sine of the solution of the homogeneous equation plus the particular solution, which is what we found, over omega 0 square minus n square omega square sine. Notice the frequencies are different. This is n omega t. So here we have the multiples of the driving frequency. Here we have the natural frequency, and this is because that we are putting is linear combination of solution of the homogeneous equation plus the particular solution. That's what we are doing, what we always did. And now we impose the initial conditions. The first condition, of course, is going to kill that cosine that shouldn't be there. So initial conditions, 0 has to be equal our solution at 0, and this is going to be C1 times 1 plus C2n times 0 plus 0. This is going to be 0, this is going to be 0, and this here is going to be 1. So, of course, the first condition kills C1. Great. So now what we have is actually not this whole function. We have only the two last terms. Copy, paste. So I'm going to put it here. And now, happily, I'm going to erase this term that is not there and move everything to the front. So this is the solution we are working with, a combination of two signs. And now we are going to tune this coefficient, so this function satisfies the second boundary condition, but the second boundary condition is for the derivative, so we need to compute the derivative. It's not boundary condition, it's initial condition, sorry. So we are going to have derivative of sine is cosine multiplied by omega 0 C2n cosine of omega 0 t, and here is going to be crowded. That is what is going to be. So there, and then we are going to have fn, then we are going to have n omega, then we are going to have here the denominator as before, and then this sign becomes a cosine because we are computing the derivative. And then the chain rule says, okay, derivative sign is cosine, and then we have to multiply by this coefficient, which I put it there. All right, so 0 has to be equal this derivative. And then we are going to have omega 0 C2n multiplied by 1, and then this horrible coefficient, copy, we are going to put it right here, multiplied also by 1. We compute C2n. You see, it depends on n. That's why C2 I added an subindex n. And it's going to be that horrible coefficient. And also divided by 1 over omega 0. So that's that. That is our solution. Our solution is going to have solution yn for each term is going to have the coefficient C2, which is that coefficient there, which I'm going to write it as with a negative sign. Forgot the negative sign. We need to move this thing to the other side. So negative there. All right. So we have a negative fn hat over all that omega 0 squared. Then we have the n omega over natural frequency omega 0, and then this is the coefficient C2, which multiplies the sine of the natural frequency times t, and then plus same coefficient, well, plus this, copy, paste, plus that there, and let's make it a little bit closer so doesn't look so ugly there. So this is the solution, but notice that we have this factor is the same on both terms, so I'm going to pull it common factor right away, and we are going to have a nicer formula for our solution, which is going to be this factor omega 0 squared minus n squared omega squared, and this is going to be common factor of the second term. I'm going to put it first because it's positive, so sine of n omega t. The second term is negative, so minus. We have this extra factor here, multiples of the driving frequency over the natural frequency, and then we have the sine of the natural frequency times t. And you can check that this function actually satisfies the initial conditions, both of them. So this is the solution we were looking for. So what we are saying here is that for each quantum of vibration, the spring is going to respond with this solution here. So what is the total solution? Well, we add up each term on the force, and then we know that the total solution is going to be the addition in n of all these solutions, so is this solution here. That is going to be the total solution. The addition of the individual responses for each quantum of vibration, the system responds like this. We add them up, and we have shown already in green that this is the solution. A few remarks to finish, and we are done. What happens if any harmonics of the driving frequency, we already know they are different of the natural frequency, but still, what happens if they are very, very, very close? Well, this term here is going to be very, very, very large, and we are going to be close to resonance, which is essentially, this is actually what happens in the Tacoma bridge. In Tacoma bridge, it's not that we got exactly one of the frequencies of the system, the natural frequencies equal one of these harmonics, but it was very close, and that is enough. So this term is really big, bigger than what the bridge can hold, and it broke. So we are close to resonance, and we want to avoid that if you are building something. What happens if n or any multiples of the driving frequency are much larger than the natural frequency of the system? Well, this coefficient then is going to be much larger than 1, just divide here. And then notice that this coefficient appears here. So this is going to be much larger than 1, so this term is going to be much larger than this term. This is the response of the system, recall, and this is the natural oscillation of the system. So the response for a frequency with this condition is going to be small. So essentially that part of the signal is going to be filtered out by the spring or your system. And this is what essentially we want if you are building a bridge. So the job of the engineering is always to check, does the force contain dangerous frequencies? Dangerous frequencies are these frequencies. Well, Fourier analysis is the way to answer that. So hopefully this is a nice example of what is going on, and it's a good place to stop. See you guys in the next video.